So we will to do that example 4, combine the raw reduction and the cofactor method to compute the determinant of that. So we have this much here. -1, 2, 3, 0, 3, 4, 3, 0, 5, 4, 6, 6, 4, 2, 4, 3. So we want to compute the determinant of that by use of the reduction method. So if you look at the last row here, the last column, that's many zeros. So in this case, we can increase the number of zeros by also making this one 0 here. So to make this one 0, then we use the row reduction method. So we can make this row, this value here to be 0. So to make it to be 0, then what you can do is, let's say to get the new R3, then it should be R3 minus 2 R4. R3 minus 2 R4. So you want to make this 6 here to be 0. So here now what you get is determinant of -1, 2, 3, 0, 3, 4, 3, 0. So our new R3 here will be R3 minus 2 R1. So here is R3 5 minus 8. You get what? Minus 3. 4 minus 4, you get 0. 6 minus 8, you get minus 2. And then 6 minus 6, you get 0. And this remains the way it is. Now you use the cofactor. So you already have all these zeros. Then you can now delete this and this. So you use this as the value there. So what you can do now is, now we have 3 multiplied by -1. And this one is what? At the point, the row 1, 2, 3, 4, the row 4 plus the columns are 1, 2, 3, 4. The column is 4. -1, 4 plus 4. And then now the determinant of, you've deleted this and this. So the determinant of -1, 2, 3, 3, 4, 3, and then -3, 0, and -2. Okay, so that's how we do it. Now, again, this has a 0 here. Now, since this has 0 here, then you can also use a reduction method. You can still make this one to block. So you can make this. Okay. So this case, then this is equals to, so since this one is even, then we have our 3 there, and then the determinant of -1, 2, 3, then 3, 4, 3, -3, 0, and -2. So we want to make this to be what? To be 0 here. So to get our new R2, yeah. So it is R2 minus what? -2 R1. R2 minus 2 R1. So we want to make this one to be 0. So here you have our 3 there, and then minus 1, 2, 3. So add 2. So 3 minus 2 here will give us what? Will give us 5. 4 minus 4 will give us 0. 3 minus 6 will give us minus 3. And then this remains the way it is. And minus 2 there. Okay. Now, using the cofactors again, then we delete this and the first column there. So it will be equals to 3. And then 3 is the one which is outside here. So we have our 2 there multiplied by -1. We are deleting the first row, plus we are also deleting the second column, plus 2 here. And then now we are deleting this and this. So we have 5, we have -3, we have -3, and then we have -2 there. -2 there. Okay. So now it has become a 2 by 2. Now it becomes so easy. So finally, this is equals to, since this one is even, so it means it will be a negative. So what do you get here? So you get 2, so -6. And then the determinant here will be what? Multiplied by 5 multiplied by -2 minus -3 multiplied by -3. And finally, this is equals to -6 multiplied by -10 minus -9. -10 minus 9. And finally, this will give us what? 114. So that is how you can combine the reduction and the cofactors. Any question? Okay, remark. If A is an n by n matrix, then and K is a scalar, then determinant of KA, is equals to K raised to n determinant of A. K raised to n determinant of A. This one is so important. Determinant of K is a scalar. Then determinant of Ka is similar to K raised to, if it is an n by n. If it is a 3 by 3, then determinant of Ka equals to K raised to 3 determinant of. If it is 4 by 4, then K raised to 4 determinant of. Okay, now let's come to the next section here, section number 2, properties of determinants. Properties of determinants. 2.1, a theorem which we will not prove. We have proved by the examples. Theorem. An n by n matrix A is invertible if and only if determinant of A is not equals to 0. So if the determinant is not equals to 0, then it means the matrix is invertible. It's invertible. So if it is 0, then it is not invertible, or it is singular matrix. So the examples are the ones which we have done. So like this one, we're getting the determinant is 114. So this is invertible, like the ones which we have done previously. So all those, so long as it is not 0, then the determinant it is invertible. It is invertible. Can give you a simple example here. Show that. So example 5. Show that matrix A, which is equals to -1, -1, 0, 2, 1, 0, 1, -1, -3 is invertible. So here, what we need to know is we need to check whether determinant of A is not equals to 0. Determinant of A is not equals to 0. So here, the determinant of -1, -1, 0, 2, 1, 0, 1, -1, -3 is equals to, so since the last column there has many zeros, then we can use a cofactor method. So in this case, we have -3 and then -1 raised to, we are deleting the third row plus the third column there. And then determinant of -1, -1, 2, and 1. So here, what we get is, so this is -3, this is 6, which is even. So we have -3 there, and then -1 multiplied by 1, -2 multiplied by -1. And this will give us -3, -1, -2, which is +2. And this will give us -3. This will give us -3. This -3 is not what? It's not equals to 0. It is not equals to 0. So it means that matrix is invertible. It's invertible. (2.2) theorem. If we have the vectors v1, v2, all the way to, let's say, vn, and these are elements of Rn. We have those vectors which are elements of Rn. These are linearly independent if and only if determinant of v1, v2, vn is not equals to 0. Is not equals to 0. So if we still remember linearly independent. So if it is linearly independent, then we have what? Trivial solutions on, right? We have trivial solutions. So it means all the columns have free or basic variables. I mean, they don't have any free variables. So we have pivot positions in each of the columns and the rows. Now, for another way of knowing that the vectors are linearly independent by getting the determinant. So you can put it in a matrix form, and then you get a determinant. You get a determinant. So the proof of this is that when you use the inverse matrix theorem, which we've done it above, so this is actually the theorem 2.1 is the inverse matrix theorem. Then V1, V2, Vn are linearly independent if and only if this matrix here, which we form from the vectors Vn here, is invertible matrix. Is invertible matrix. Means that determinant of V1, V2, Vn is not equals to 0. It's not. For example, example number 6. Determine whether the vectors are linearly independent or linearly dependent. Linearly independent or linearly dependent. And the vectors are 4, 6, minus 7, minus 7, 0, 2, then minus 3, minus 5, and 6. So determine whether those vectors are linearly independent. So for this to be linearly independent, then you need to get a what? You put it in a matrix form. So you put this one in a matrix form. So V1 is 4, 6, minus 7. V2 is minus 7, 0, and 2. And then V3 is minus 3, minus 5, and 6. 3, minus 5, and 6. So what you get here as a determinant. So determinant, if we let this one to be A, so our determinant of A is equals to 11, which is not equals to 0. So therefore, this is what? This is linearly independent. Linearly independent. That not equals to 0. So those vectors are linearly dependent. Any question after that? Okay, example number 7. Find determinant of B and determinant of B transpose, where B is equals to 1, negative 1, negative 3, 1, 1, negative 5, and then 2, minus 2, minus 5, 2, minus 2, minus 5. So find the determinant of B and also find the determinant of B transpose. So in this case, to get a determinant of B, then we can use the cofactors method. So we can actually use the cofactors method along, let's say, this row, along column, this column. So when you use it along that column, then what we have is, if we use this along this column here, so we have 1 multiplied by -1, and then we are deleting the first row and the first column. So 1 plus 1, determinant of 1, -5, -2, and -5 there. Plus, since we are using the first column here, so we take this one again, 1, multiplied by -1, we are deleting the second row and the first column there, 1. And then determinant of -1, -3, -2, -5. Plus, we take this 2 here, 2 multiplied by -1, we are deleting the third row plus the first column, determinant of -1, -3, 1, and -5. 1 and -5. So when you solve these, then this is equals to 1, and then multiplied by -5 -10, plus this is -1 multiplied by 5 -6, plus this is 2 multiplied by 5 plus 3. 5 plus 3. So this is -5, and then this is -2 multiplied by -5 is 10, right? So, and there was a minus here, so it's a minus. So finally, what you get is 2. Now, if we do the transpose, then the B transpose here, we now transpose, then we have 1 -1 -3, 1 1 -5, and then 2 -2 -5. So that is a transpose. Now, to get the determinant, then you can do what? You can also use the first row. So you can use the first row. So the determinant, then determinant of B transpose is actually the same as determinant of B, which is equals to 2. So they are the same. Now, since you can still come and use the first row, you can use the first row. Here we use the first column. So here you can come and use that also. You will still get the same determinant. You still get the same determinant.
So if we were to use the row in the first one, we have to use the column.
No. No, it doesn't matter. So you can use this. You can use this row. And then also, when you come to this, you can use any other. So what you want to know is, at the end of the day, when you do the determinant of B, it is the same as getting the determinant of B transpose. So you can actually use any column. You can use this. And then when you come to the transpose, you can either use rows or you can still get the same answer. Okay. Now, if we come to another example, example number 8, find determinant of A multiplied by determinant of B and determinant of A, B, where A is equals to -1, -1, 0, 2, 1, 0, and then 1, -1, -3. And our B is equals to 1, -1, -3, 1, 1, -5, then 2, -2, and -5. So we have already done the determinants here. So we found that determinant solution, determinant of A was equals to what? -3, right? And determinant of B is equals to 2. Is equals to 2. Then determinant of A multiplied by determinant of B is the same as -3 multiplied by 2, which is equals to -6. Now, when you multiply the two matrices, then when you multiply A, which is -1, -1, 0, 2, 1, 0, 1, -1, -3, and 1, -1, -3, 1, 1, -5, and 2, -2, and -5. So when you multiply the two matrices there, then what you get is -2, 0, 8, 3, -1, -11, and then -6, 4, 17. 6, 4, 17. So this is A, B, each equals to A, B equals to that. Now, when you come and do the determinant here, then determinant of A, B, since we've done a lot of determinants, then what you get is equals to -6. Therefore, this will lead us to the theorem this will lead us to the theorem 2.3 theorem, whereby if A and B are n by n matrices, then determinant of A transpose is equals to determinant of A, and determinant of AB is equals to determinant of A multiplied by determinant of B. Any question? For example, example number 9. Find the determinant of the matrix. 1, 0, 0, 7 minus 2, 0, minus 9, 11, and 3, multiplied by 2 minus 6, 7, 0, 3, minus 8, 0, 0, and 4. 0, 0, 4. Find the determinant of the matrix. So this is actually the same as multiplication. So to get a determinant of this, then so determinant of this is actually the same as getting the determinant of one, 0, 0, 7 minus 2, 0, and then minus 9, 11, and 3, multiplied by determinant of 2 minus 6, 7, 0, 3, minus 8, 0, 0, and 4. It is the same as getting the determinant vector. So therefore, since the two matrices are upper triangle, lower triangle, then you can just multiply the what? The main diagonals there. So then determinant here, so this is equals to 1 multiplied by minus 2 multiplied by 3, and then multiplied by this is equals to 2 multiplied by 3 multiplied by 4. And finally, what you get here is minus 144. Minus 1. So this is for this and this one. .4 here. Now, if A is an invertible n by n matrix, then determinant of A inverse is equals to determinant of A, and then you get the inverse. Determinant of A inverse is equals to A and the inverse. So basically, this is the same as determinant of A inverse is the same as 1 over determinant of A. 1 over determinant. So this is actually. So how can we prove this? So let's prove. Now, using the inverse method, so we can say that if we have the A and A inverse, yeah, A and A, if you multiply the matrix A by its own inverse, what do you get? You get the what? Identity matrix, right? You get the identity. Then, if you do the determinant here, determinant of A inverse is also equals to determinant of identity. So if you put the inverse in each one of them, so A inverse is the same as identity. Then, using the theorem that we've just done for the invertible matrix, then here, then determinant of A inverse is the same as determinant of A multiplied by determinant of A inverse, which is equals to what? Which is equals to determinant of identity. And identity is what? It's just 1, 1, 1 at the time. So basically, determinant of identity is equals to what? Is equals to what? So then, when you divide both sides by determinant of A, then determinant of A inverse is equals to 1 all over determinant of A, which is also equals to determinant of A inverse. Okay. Any question up to it? Okay. For example, example number 10. Find a determinant of A raised to 4 and determinant of A inverse, where A is equals to 2 minus 2, 5, 0 minus 1 minus 3, and then 0, 0, and 1. 0, 0, and 1. One. Okay. Now, if you look at if you look at this, if you look at this, then we said that determinant of A inverse, yeah, is equals to determinant of A, and then you inverse this, right? Right. Then determinant of A raised to 4, okay, is now the same as determinant of A, and then you do what? You raise 4. Okay. So determinant of A raised to 4 is similar to that. So we are actually getting it from this. So determinant of, let's say, A raised to 2 is the same as determinant of A, and then B raised. Okay. Now, in this case here now, determinant of our A here is equals to what? So we can just multiply that, since this one is a triangular matrix. So this is equals to 2 minus 1 minus 1 there, which is equals to minus 2. Minus 2. Then, now, determinant of A raised to 4 is now equals to determinant of A, and then you raised to 4, which is equals to minus 2 raised to 4, which is the same as what? 16. Now, what about the inverse? The inverse, we just do the same way here. Now, since determinant of we carry from this, so determinant of A inverse is the same as determinant of A, and then you inverse, which is now equals to our determinant of A is minus 2. And then when you inverse this, then this is the same as what? Minus 1 over 2. Any question? Any question? Okay, there is no question. Then let's still have like 10 minutes. Now let's now come to the last section in chapter 3. Which is 3.3, and this is the Cramer's rule, volume, and linear transformation. So what you just do is a Cramer's rule. Okay, let's look at 1.1. What is a Cramer's rule? You know, if you've done some business maths, then maybe you've done this. So Cramer's rule, we let A to be equals to the vectors, which are A1, a linear combination, A2, up to, let's say, AN. Yeah. So these vectors here can be the vectors which you get from the coefficients of the linear equation. B, an invertible n by n matrix. So it should be invertible. That means we should get the determinant. We should get the determinant. And if B is our solution, which is an element of Rn, then we now define AJ B to be equals to A1 up to AJ minus 1, B, AJ plus 1, and then up to AN. So J equals to 1, 2, up to J equals to 1, 2, up to. Now AJ. So AJ here. So we actually replace the vector AJ by our B. Okay. So since this one is A1 up to AJ minus 1, there was AJ here. But we can replace it with vector. Okay. We replace with that vector B. Then the matrix equation AX equals to B, where X equals to X1 up to Xn has a unique solution given by Xj equals to determinant of AJ B all over determinant of A for J equals to 1, 2, up to N. Now, let's say you have a linear equation with two variables, let's say x1 and x2. Now, if you want to get x1, then x1 is equals to determinant of a1b all over determinant of a. To get x2, then determinant that is x2 equals to determinant of a2b all over determinant of a. So to get x1, then what you do is you replace or you remove the vector from the matrix A and replace it by B, and then you get it all over determinant. To get x2, then you remove the second vector in the matrix A and you replace it by B, and then you get a determinant. Then you write of A. Determinant of A. So I don't want to write for you the proof for this because it will not be of any use, but you can still look at it from your textbook. So let's look at an example. For example, example number 1. Use Hammer's rule to solve the following linear system. So if we have minus 5x1 plus 3x2 equals to 9, 3x1 minus x2 equals to minus 5. Now, here we need to set A and B. So the solution. So we set A to be equals to the coefficients here, which is minus 5, 3, 3, minus 1. And then our B is equals to 9 and what? Minus 5. 9 and minus 5. Now we want to get now A1B and A2B. So to get A1B, then A1B is the same as A1B is the same as replacing this first column here by this. Okay. So A1B is equals to 9 minus 5 and then maintaining 3 and minus 1. A2B is the same as maintaining the first one, which is minus 5 and 3, and replacing 3 minus 1 by 9 and minus 5. And then you do what? You get a determinant. So the determinant of A is equals to minus 5, 3, and minus 1, which is the same as what you get is minus 4. Now, determinant of A1B is equals to getting the determinant of 9 minus 5, 3, and minus 1. And this is equals to 6. And determinant of A2B is equals to determinant of minus 5, 3, and 9, and minus 5, which is equals to minus 2. Therefore, to get now x1 is equals to determinant of A1B all over determinant of A, which is equals to determinant of A1B is 6, all over determinant of A here is minus 4. X2 is equals to determinant of A2B all over determinant of A, which is equals to minus 2 all over minus 4. So our x1 is equals to minus 3 over 2, and our x2 is equals to 1 all over 2. So that is how. So what you do, you set A to be the coefficient here. That's the way we did the coefficient matrix. So this is the coefficient matrix. And then we set our B to be that. Now, A1B is you replace the first vector here. B is this. A to B, you replace the next one. Yeah. So if you know that 3 by 3 is the same thing. If these are 3 variables, then you take the first one, replace the second one, replace the third one, replace, and then you get the determinants. You get now x1 is determinant of these divided by determinant of A, get that. So that is how simple it is. Okay. I'll see you on Wednesday.
Do you have notes for the Friday before the rain?
You want the one for Friday?
Yeah.
Yeah, you can go to my office and then I give it to you. You want to take this? Okay.